Welcome again, chemistry students. This video focuses on lesson 5 of your General Chemistry 1. This is entitled Gas Laws. For the objectives, we will define pressure, give the common units of pressure, and use the gas laws to determine pressure, volume, or temperature of a gas under certain conditions. So first, let's define a gas. What is a gas? A gas is a kind of matter with particles that are widely separated from one another. As you can see in this illustration, we have gas particles that are separated and tend to push one another and against the wall of the container. Let's have the common properties of gas. One is particles are widely separated. As you had seen in the previous slide, particles in gas, unlike in solids and liquids, they are widely separated. Gases also do not have definite shape and volume. Like liquids, according to the shape and volume of the container are the shape and volume of the liquids. Gases also have low density. This is due to small number of particles that occupy a given volume or space. They are highly compressible because of wide separation and large spaces between particles. They exert pressure. This is a result of the bumping, the pushing against one another. They also rapidly diffuse because of the free motion of particles. They also do expand when heated because of increased kinetic energy when heated. And they are readily soluble because of the free motion of the particles. The dry air is composed of the following gas particles or gas molecules. The most abundant in dry air is nitrogen gas. It takes about 78.08%. Oxygen is about 21%, argon 0.93%. Other gases such as carbon dioxide, neon, helium, methane, and krypton also are present in the dry air, and other gases in trace amounts such as xenon, hydrogen, dinitrogen monoxide, and few others. How do gas molecules behave according to the kinetic molecular theory? According to the assumption of the kinetic molecular theory, gases consist of tiny subatomic particles called molecules. So when referring to gas particles, you use the term as the representative units of gas particles, molecules. So you say oxygen molecules, nitrogen molecules. So when referring to the particles of gases, we use the term molecules. Number two, the distance between particles is large compared to the size of the particles themselves. So much smaller are the sizes of the gas particles compared to the spaces between them. Three, gas particles have no attraction with one another. They may tend to bump or collide with one another, but they do not attract one another. There are no forces of attraction between and among the particles. 4. Gas particles move in straight lines in all directions, colliding frequently with one another and with the walls of the container. So as I said, because of the free motion and the wide spaces between particles, they tend to collide with one another and against the walls of their container. Number 5 theory, no energy is lost by the collision of a gas particle with one another or with other particle with the walls of the container or collisions are perfectly elastic. In physics, you discussed the three types of collision. We have perfectly elastic, inelastic, and superelastic. So the type of elastic between particles is perfectly elastic. This is a result of complete transfer of kinetic energy from one moving particle to the other particle. And the last one, the average kinetic energy of particles is the same for all gases at the same temperature, and its value is directly proportional to the Kelvin temperature. So all gas particles, whether oxygen, carbon dioxide, nitrogen gas, or any other gas, they have the same average kinetic energy given that they are in the same or at the same temperature. What is kinetic energy? Kinetic energy is the measure of half the mass of the gas multiplied by the square of velocity. So as you can see here in the equation, we have Ke for kinetic energy that's calculated as 1/2 of the mass of gas multiplied by the square of the velocity of the gases. What about pressure? So we have kinetic energy as the um, half the mass of gas times the square velocity. Pressure is another characteristic of gas particles. Pressure is defined as the amount of force per unit area. So you will see in the equation here, we have pressure equals the amount of force exerted per unit area. Pressure exerted by a gas depends on the following: the number of gas molecules or particles. So the greater the mass, the greater the tendency for collision, the greater the pressure. Temperature of the gas, the higher the temperature, the higher the amount or value of kinetic energy, the higher chances for collision. So pressure also is higher. And another one, we have volume. Volume is dependent also on the space. So the smaller the space, the more collision, the greater the pressure. What about the concept of STP? STP stands for standard temperature and pressure. Standard pressure is 1 atm. Standard temperature is at 273 Kelvin. Whereas the volume of 1 mole of any gas at standard temperature and pressure is always equal to volume of 22.4 liter. Take note that the pressure of a gas is a result of the collision between the gas molecules with one another and against the walls of the containers. As I said, because particles are in constant motion and are separated by wide spaces, they tend to bump or collide with one another and against the wall of the container. This collision results to the formation of pressure. The following are some common units of pressure. We have atmosphere, millimeters of mercury, torr, Pascal, and few others. The standard pressure of 1 atm is equivalent to, take note, 760 torr, 760 millimeters mercury, 101.325 kilo Pascal, 14.7 pound per square inch, and few others. So I have here illustrations wherein you will see the same volume and temperature. Volume is the same as 1 liter or 1000 milliliter, and temperature of 0. So they have this different temperature. The first one has 0 degrees Celsius and the other one 100 degrees Celsius. Okay, let's have the conditions. At lower temperature, we have lower pressure. At higher temperature, there's also high pressure. Again, what causes higher temperature when higher pressure when temperature is higher? Higher temperature results to higher amount of kinetic energy. So the more collision between particles, the higher the amount of pressure. As pressure is a result of collision. We have the following gas laws to explain the behavior of gases. We have Boyle's law, Charles' law, Gay-Lussac's law, combined gas law, Dalton's law of partial pressure, Graham's law of diffusion, and the ideal gas law. Let's start with Boyle's law. Boyle's law states that at constant pressure, the volume of a fixed gas, a mass of gas, is inversely proportional to the pressure. So in the 7 gas law, you will see relationships. It's either direct proportion or inverse proportion. Between pressure and volume, the relationship at constant temperature is inversely proportional. What does it mean? When volume is decreased, pressure is increased. And vice versa. When pressure is decreased, volume must be increased. So that's what we mean by inverse proportion. As one quantity increases, the other will decrease. As the other decreases, the other will increase. So they have opposite effects. So in equation, we have volume as inversely proportional to pressure. In equation, we have the product of the initial pressure and volume must be equal to the product of the final pressure and volume. Let's have this graph. So you will see across the x-axis are the volumes in liters. On the y-axis, you will see the pressures in ATM. So notice the initial pressure of 8 ATM across the initial volume of let's say 0. After increasing the pressure, let's say we increase the pressure to 5 liters, you'll see the decrease in pressure when the volume is increased. Why is this possible? Because when you increase the space for the gas particles, you are decreasing the chances for collisions. As I said earlier, the smaller the amount of collision, the smaller the pressure. The greater the amount of collision, the greater the pressure. Increasing the space or volume means increasing the space for the gas particles to move, and therefore less collision. So you are decreasing the chance for collision, therefore you are decreasing the amount of pressure. And that again happens when you increase the volume. So increase in volume means decrease in pressure, and therefore the relationship is inverse proportion. Let's have a problem. An 8-liter sample of nitrogen gas is at a pressure of 500 torr. What must be the pressure to change the volume to 3 liter? Considering that the temperature is constant, we notice a decrease in volume. So we have 8 liter to decrease to 3 liter. So what should happen to 500 torr as initial pressure? If volume is decreased, then we expect pressure to increase because the relationship between volume and pressure is inverse proportion. So if there is an increase in volume, there must be a decrease in pressure. Let's find out. So to solve this problem, let's do the following steps. Step 1 is to identify the information given. The information given are as follows. We have initial pressure of 500 torr, initial volume of 8 liter, and final volume of 3 liter. What we are looking for is the final pressure. So, given the Boyle's law equation, P sub 1, V sub 1 equals P sub 2 times V sub 2, we derive P sub 2. So, to derive that is to simply transpose final volume to the other side. So we will have P sub 2 or final pressure left in one side of the equation. So transposing V sub 2 to the other side, we will derive the formula P sub 2 equals P sub 1 times V sub 1 over V sub 2. Next step is to substitute the given information or data into the equation and solving the problem. So the initial pressure given is 500 torr. The initial volume is 8 liter. The final volume, as in the denominator, you have 3 liter. So cancelling the same unit between numerator and denominator liter, you will have torr as the remaining unit. Torr, which is the unit of pressure which we are looking for. So doing the operation 500 times 8 divided by 3, you will have 1.33 times 10 raised to 3 or exponent 3 torr. Let's see. Let's analyze. Again, the initial volume is 8 liter. The final volume is 3 liters. So notice a decrease. So if the relationship between pressure and volume is inverse proportion, the initial pressure of 500 torr must be increased. Okay? Because you decrease the volume, you decrease the space, or you lessened or made the volume or the space for the particles to move. So decreasing the space for the, reducing the space for the particles to move is increasing the pressure because you are increasing the chances for collision. The greater the chance for collision, the greater the pressure. So 1.33 times 10 raised to 3 is about, move the decimal point to the right. So this is equivalent to 1,333 torr. So from 500 torr, it increased to 1,333 30 torr. So that indeed is an increase in volume as a result of decrease in increase in pressure as a result of decrease in volume. Let's have the second law. The second law is Charles' law. It states that at constant pressure, the volume of fixed mass of gas is directly proportional to the absolute temperature. If Boyle's law gives us an inverse relationship between pressure and volume, this time we have volume temperature relationship, indirect proportion relationship. What does that mean? When you increase one, you increase also the other. If you decrease the one, you also decrease the other. Let's find out. In equation, we have volume as direct proportional to temperature. In the mathematical equation, we have the ratio of the initial volume to initial temperature is equal to the ratio of final volume to final temperature. So you have here ratio equals ratio. We have here another graph. This time we have temperature across the x-axis, along the x-axis, and volume along the y-axis in liter. Temperature in degrees Celsius. So let's have the initial temperature of, negative 100. So at negative 100, the volume is 1 liter. You increase the temperature to 100 degrees Celsius. So that's an increase of 200 degrees Celsius because it's from 100 to become 0, you have to increase by 100, and to increase to another 100, you have to increase by another 100. So that's a decrease or difference of 200 degrees Celsius. So from negative 100, it went up to 100 degrees Celsius. From the initial volume of 1, it also increased to, so along the y-axis, we have 3 liters, approximately 3 liters. So increasing the temperature from negative 100 to positive 100 degrees Celsius is also increasing the volume from 1 liter to 3 liter. So that indeed is a direct relationship between volume and temperature. We have here an illustration showing the increase in volume. So we have here in illustration A, only half of the container is filled with gas particles. You increase the volume, you double the volume, you also double the space for the particles. So this is explaining how pressure will affect the increasing volume will result to pressure. So increase in volume means decrease in pressure because you are giving the gas particles more space to move around. Okay, let's have this example. We have 255 milliliter sample of nitrogen at 75 degrees Celsius is confined at a pressure of 3 atmospheres. If the pressure remains constant, what will be the volume of the nitrogen gas if its temperature raised to 250 degrees Celsius? So notice an increase in temperature from 75 degrees Celsius to 250 degrees Celsius. So what should happen to the volume? So the initial volume is 255. So as we have said, the relationship is direct proportion. So if there is an increase in temperature, there must be an increase also in volume. So let's find out. Let's answer the problem by first identifying the given. So the given quantities, we have initial volume of 255 milliliter, initial temperature of 75 degrees Celsius. In Kelvin, we have to always convert degrees Celsius to Kelvin before we substitute them in our equations. So final temperature 250 degrees Celsius converted to Kelvin is 523 Kelvin. Again, you do that by simply adding 273, constant 273 to convert degrees Celsius to Kelvin. Step 2, let's write the equation for the unknown. So, given the Charles law equation, V sub 1 over T sub 1 equals V sub 2 over T sub 2, we derive V sub 2. So, we do that by transposing T sub 2 to the other side to leave volume 2 in one side. So, in the left side, we have V sub 2 left equals, we have transpose T sub 2. So, we shall have in the numerator V sub 1 times T sub 2 over T sub 1 as our equation for this particular sample. Let's now substitute the given and solve the problem. So, the initial volume is 255 milliliter. Let's multiply that by the given final temperature of 523 Kelvin divided by the initial temperature of 348 Kelvin. Let's do cancellation between Kelvin and Kelvin in numerator and denominator, multiplying 255 by 523 and dividing the product by 348, we shall have 383 milliliter. Let's now analyze. Again, the initial temperature is 75 degrees Celsius. It went up or increased to 250 degrees Celsius. So, since there's an increase in temperature, there should also be an increase in volume because the relationship according to Charles' law is direct proportion. So, from the initial volume of 255, what happened after the increase in temperature? It went also up to 383 milliliters. So, there is also an increase from 255 milliliter to 383 milliliter. The relationship indeed between volume temperature is direct proportion. Let's now move on to Gay-Lussac's law. Gay-Lussac's law states that the pressure of a fixed mass of gas at constant volume is directly proportional to the Kelvin temperature. So, just like Charles' law, the relationship here is direct proportion. So, if in Charles' law, we explain the direct proportion relationship between volume and temperature, here in Gay-Lussac's law, we have the relationship, direct proportion relationship between pressure and temperature at constant volume. So, we shall have the same equation, P sub 1 ratio equals ratio P sub 1 over T sub 1 equals P sub 2 over T sub 2. Let's have a sample problem. At a temperature of 40 degrees Celsius, an oxygen container is at a pressure of 2.15 atmospheres. If the temperature of the container is raised to 100 degrees Celsius, what will be the pressure of oxygen? So first, let's identify the given. We have 21.5 atm as the initial pressure. The initial temperature is 40 degrees Celsius converted to Kelvin. It's 313 Kelvin. And we also have final temperature of 100 degrees Celsius converted to Kelvin, we have 373. So we have here an increase from 40 degrees Celsius to 100 degrees Celsius temperature. So if the relationship is also direct proportion between pressure and temperature according to Gay-Lussac's law, then the initial pressure of 21.5 atm must also increase. Let's see. Okay. So using the equation P sub 1 over T sub 1 equals P sub 2 over T sub 2, we derive P sub 2. So to derive P sub 2 is again transposition. Transpose T sub 2 to the other side to leave P sub 2 left, to have it left in one side of the equation. So we have P sub 2 equals, we have transposed T sub 2 with P sub 1 in the numerator. So we have P sub 1 times T sub 2 over T sub 1. Substituting the given, we have the initial pressure of 21.5 atm multiplied by the final temperature 373 Kelvin divided by the initial temperature of 300 Kelvin. Cancelling the units Kelvin between numerator and denominator, multiplying 21.5 times 373 and then dividing the product by 313 will give us the answer 25.6 atm. Let's compare now the changes in both temperature and pressure. So again, in the equation, we have an increase in temperature from 40 degrees Celsius to 100 degrees Celsius. So if the relationship again is direct proportion, the initial pressure must also increase. So the initial is 21.5 atm. The final temperature as calculated is 25.6 atm. So there is also an increase in temperature, in pressure, because again, this is the result of increase in temperature. Why is it that pressure is increasing as temperature is increasing? Increase in temperature means increase in kinetic energy. The more mobile, the higher the kinetic energy of the gas particles, the more chances for collision. The greater the amount of collision, the greater the pressure. So that's what we mean by direct relationship, the same effect, and increase, decrease. Okay? Let's now have combination of the three. Okay, so correction here, we have combined gas law. Combined gas law is actually the combination of Boyle's law, Charles' law, and Gay-Lussac's law. So we have the equation P sub 1 times V sub 1 over T sub 1 equals the product of P sub 2 and V sub 2 divided by or over T sub 2. So if we are to analyze this, we have here, we can get here the Boyle's law, we can get the Charles' law, and we can get the Gay-Lussac's law. Or the three, when combined, we will have the equation for combined gas law. Okay, let's have an example. A sample of hydrogen gas occupies 465 ml at STP. If pressure is increased to 950 torr and the temperature is decreased to negative 15 degrees Celsius, what would be the new volume? So we have here the following given. The initial pressure is 760 torr, and then the final is 950 torr. So there's an increase in pressure. Volume is 465 initially, and we are looking for the new volume. What will be the new volume when pressure and the temperature are changed? The initial temperature is 273 Kelvin, and the final is 258 Kelvin. There is a decrease in temperature while an increase in pressure. So what should happen with the volume? Converting the temperatures in Kelvin, we have just convert them by adding 273. Let's solve the equation. Let's solve the problem using the equation of combined gas law. So again, we have the combined gas law P sub 1 times V sub 1 over T sub 1 equals P sub 2 times V sub 2 over T sub 2. Deriving V sub 2, we have to do another transpositions. So this time, we will transpose two quantities. So first, we have to transpose P sub 2 to the other side. So P sub 2 will go with T sub 1 in the numerator, in the opposite, in the other side of the equation. While T sub 2 will be transposed to the other side together with, it will be together with P sub 1 and V sub 1. So as the final equation for V sub 2, we have V sub 1 times P sub 1 times T sub 2 divided by P sub 2 times T sub 1. Substituting now the given, we have the initial volume is 465 milliliter. The initial pressure is 760 torr. The final temperature is 258 Kelvin divided by 950 torr is the new pressure divided by, multiplied by the initial temperature of 273 Kelvin. Cancelling the similar units between numerator and denominator, we shall have 465 times 760 times 258 divided by the product between 950 and 273. Doing the operation, we will have the answer 352 milliliter. So from the initial volume of 465 milliliter, it will be decreased to 352 milliliter. This is due to decrease in pressure and increase in, decrease in temperature and increase in pressure. There. Let's now go to mixtures of gases. When we have a mixture of gas, we can use the Dalton's law of partial pressure, which states that the total pressure of a mixture of gases is the sum of the partial pressures exerted by each of the gases in the mixture. So in equation, you are simply adding the partial pressures exerted by the component gases. So we have P, total pressure equals the sum of partial pressure exerted by gas 1 plus the partial pressure exerted by gas B, and so on and so forth. Let's have a simple example. A container contains helium at a pressure of 0.50 atm, neon at a pressure of 0.60 atm, and argon at a pressure of 1.30 atm. What is the total pressure in the container? So using the equation, total pressure equals the sum of the three. We have partial pressure exerted by helium plus the partial pressure exerted by neon and plus the partial pressure exerted by argon. Substituting the partial pressures of the exerted by each of the gases, we have 0.5 atm plus 0.6 atm plus 1.30 atm. Getting the sum, you will have 2.40 atm. And also, you can use Graham's law of diffusion. Graham's law of diffusion is used when comparing two gases in a mixture. It states that the rates of diffusion of two gases of the same temperature and pressure are inversely proportional to the square roots of their densities or molar masses. So we have the equation rate of diffusion of gas A over rate of diffusion of gas B equals the square root of the ratio between the density of the two or the molar masses of the two, gas B and over gas A. But first, let us distinguish between effusion and diffusion. Effusion is a process by which gas molecules pass through a very small opening from a container at a higher temperature to one at lower temperature. It's like opening a bottle of perfume. When you open the bottle, gas particles will escape through the opening of the bottle. So that small opening will be the outlet, will be where the gas particles will escape from the system of mixture. What about diffusion? Diffusion is the ability of two or more gases to mix spontaneously until they form a uniform mixture. So after the gas particles escape from the bottle of perfume, these gas particles will spread throughout the available space until such time that it has uniformly mixed with other gases. So we have here illustrations. We have two gases here, namely bromine and dry air. So when the cock is closed, there are no particles escaping through that opening. When you open the cock, bromine particles will transfer to the other side, to the other container, to the original container of air. And at the same time, gas particles in air will also escape through the opening and go to bromine until such time that the gas particles are widely, uniformly mixed with other gases in the container. Yes. So closing and opening the stopcock will allow effusion and diffusion of gas particles. Let's have an example problem. What is the ratio of the rate of diffusion between carbon dioxide and carbon monoxide? So between the two, which diffuses faster than the other? Effuses or diffuses faster than the other? To compute this is to use the equation that we have flashed earlier. First, when comparing rate of diffusion between two gases, you have to identify which is gas 1 or gas A and which is gas B. Gas A is usually is always labeled as gas 1. So it's always the lighter gas particle. The heavier is always labeled as gas B or gas 2. So in this case, carbon monoxide is 28 gram per mole. So molar mass or molecular mass, formula mass of carbon monoxide is 28 gram. That is 12 gram of carbon plus 16 gram of oxygen to give us 28 gram. Carbon dioxide, we have 1 carbon 12, 2 oxygen atoms, 16 times 2 will give us 32 plus 12. We will have 44 gram for carbon dioxide. So the lighter one is 28 gram carbon monoxide. So that will be our gas A. Gas B will be the heavier gas, which is carbon dioxide in this problem. So to solve to answer the question, let's substitute the given molar masses. The molar mass of gas B is 44 gram divided by the molar mass of gas 1 or carbon monoxide, we have 28 gram. We cancel gram and divide 44 by 28 and square, getting the square root, we have 1.25. To interpret which between the two is lighter and will tend to effuse or diffuse faster, of course, it's the lighter gas. It's like humans. Those heavier by weight can move less freely than those lighter weight people. So like in basketball, the lighter the those small players usually are the point guards because they are expectedly faster to move or to run the ball from one side of the court to the other. So it's like gas particles. The lighter the gas particle, the faster it will effuse or diffuse. So in this case, between the two, carbon monoxide and carbon monoxide diffuses or effuses 1.25 times faster than carbon dioxide. So that's how we use the answer 1.25 in interpreting which of the two is effusing or diffusing faster than the other. So again, that's carbon monoxide diffuses or effuses 1.25 times faster than carbon dioxide. Let's have the density of gases. Density is computed as mass over volume. Remember that all gases at the same temperature occupies the same volume of 22.4 liter. 1 mole of any gas at the same temperature occupies 22.4 liter. The density of neon at STP is 0.9 gram per liter. What is the molar mass of neon? To get the molar mass of neon, you multiply the density of neon, which is 0.9 gram per milliliter, per liter, times the volume of 1 mole, which is 22.4. And then cancel the units liter between numerator and denominator. So you will get the ratio gram per mole, which is the unit that we are looking for here. So 0.9 times 22.4 will give us 20.9 gram per mole is the molar mass of neon. The molar mass of sulfur dioxide is 64.07 gram per mole. Determine the density of sulfur dioxide at STP. So we have here the density. So 64.7 molar mass multiplied by the ratio 1 mole per 22.4 milliliter. Again, this ratio is taken from the ratio 1 mole of any gas occupies a constant volume of 22.4 liters. So in order for us to determine the density, earlier we determined the molar mass of a gas. This time, in this particular problem, we are determining the density of a gas. So given the molar mass of the substance of or gas at STP, which in this case is 64.7 for sulfur dioxide, and then multiply by the constant 1 mole per 22.4 liter. Every conversion factor can be reciprocated depending on your need to do cancellation in the problem. So in this case, we use the ratio 1 mole per or over 22.4 liter. This is to cancel the units mole and mole between numerator and denominator. So we have now the unit gram per liter, which is the unit of our density, multiplying or dividing 64.07 by 22.4, we have 2.86 gram per liter, which is the density of our substance or gas here, which is sulfur dioxide. And the last one, we have ideal gas law. Ideal gas law equation is given here as the equation, the product of pressure and volume equals the product of N, which is mole of gas, times ideal gas law constant, which is 0.0821 liter ATM over mole dot Kelvin, and temperature. So we multiply pressure and volume in one side and nRT in the other side. Let's have one simple problem. A balloon filled with 5 moles of helium gas is at a temperature of 25 degrees Celsius. The atmospheric pressure is 750 torr. What is the balloon's volume? So first, let's organize the given information. We have the given, we have the given 25 degrees Celsius. So convert that to Kelvin, we have 298 Kelvin. Pressure, we have 750 torr given. Converting that to ATM is using the fraction 1 ATM, conversion factor 1 ATM over 760 torr. Cancel torr, so we shall have 0.987 torr. And then using the ideal gas law equation PV equals nRT, we derive V by substituting, transposing to the other side. From the left side, you transpose pressure to the other side, so it becomes denominator of nRT. Substituting the given, we have the number of moles from the given is 5 moles of helium. So 5 moles times N, R, the value of R is constant at 0.80821 liter ATM per mole, Kelvin, times the temperature of 298 Kelvin, all over, multiply the product by the pressure given 0.987 ATM. So cancelling the units, we have liter left. So 5 times 0.0821 times 298, divide the product by 0.987, the answer will be 124 liter. To determine the molecular weight using the ideal gas law, we can have the following. We can consider the following. So we have the ideal gas law PV and RT. So notice nRT is the number of moles can be expanded to gram per molar mass, or capital M. So we can replace N from the gas law equation as gram per molar. And then from here, let's derive molecular weight as M, or molecular weight, equals gram of gas times the ideal gas law times temperature, divide the product by pressure and volume. So example, calculate the molar mass of an unknown gas if 0.02 gram occupies 250 milliliter at a temperature of 305 Kelvin and pressure of 0.045 ATM. So we have the equation molecular weight equals gram times ideal gas law times temperature over pressure and volume. So substituting all the given, these are all the given. Substituting them in the equation, we have 0.02 times 0.082 times 305 divided by the product of 0.045 and 0.250. Cancelling all the similar units between numerator and denominator, we shall have the ratio of gram and mole as the unit left. So doing the operation, we will have the final answer 44 gram per mole, which is our molar mass for the unknown gas in the problem. So that will be all for this lesson on gas laws. I hope you were able to refresh your knowledge about gas laws. Thank you for watching. Until next time.